Okay, everybody, hello, and let's get into the topic of the class of today, which is the topic 1.7, and it deals with properties of rational exponents, and that's going to be the first part for the first class. And for the next class, we're going to have properties of logarithms. Okay, all of this is topic 1.7. This is for one class, this is for the next. Okay, so let's get into the properties of rational exponents. Remember that the word rational means fractional. Okay, all right, so I'm gonna erase this part since we're not gonna need it, and let's talk about the properties of rational exponents. Okay, so what are going to be the objectives for today? At the end of this class, I want you to understand and be able to calculate two things. The first is I want you to understand what something like this means. When we raise a number to a fractional exponent, like for example 1/3, or another number to the 1/2, or another number to the 1/8, or another number to the 1/17, or another number -7 to the 1/100, and so on. So you get the idea, right? What are we doing here? We're raising numbers, any type of number, to a fraction, but it has a very specific form, right? It's always 1 over something. Okay, so this is the first thing you're gonna understand today. And the second thing that I want you to understand and be able to calculate is the more general case, which is any number, for example the 5 again, but to any possible fraction. For example, 5 to the 2/3, or 6 to the 4/5, or -2 to the 7/4, or -8 to the -1/2, etc. Okay, so this is the most general case in which we are raising numbers 5, 6, -2, -8, etc. to any possible fraction that we can create. Okay, so this is the most general case. By the end of this lesson, you will understand these two things. Okay, so let's go ahead. Let's lay the background for this. What things do we need in order to understand these two topics that I already told you about? We need the following. The first is, let's remember that a while ago we discovered what this symbol means, a to the n. This is nothing but a times etc. times a and times, okay? And I'm referring to the specific case in which n is a positive integer. So in the case of n, a positive integer, all that this symbol means, a to the n, is just this thing. And that is the easiest way to understand exponents. It is the easiest case to understand exponents. And we said that there was a lot of convenience in this notation because it allows you to write numbers that are very big, and I mean big in the sense of writing. For example, this number 2 times 2 times 2 times 2 times 2 times 2, you can compress this number into 2 to the 6. So it's very economical writing. That's all it is. It's a very economical way to write all of these things. Okay, so in the case of n being a positive integer, we understand what this symbol means. The next thing we did was understanding what a to the minus n means. And by minus n, I mean a negative integer. And all that this meant was this. We gave this definition. A to the minus n was going to be equal to 1 over a to the n. And we understand with this symbol, right? Okay. In here, again, I want you to understand that this is a definition. This is not this is not something that you can prove. This is something that you define. And I know that it was very hard to understand why this is a definition. Don't worry. If you didn't understand, don't worry. Just accept it as fact. And then the next thing that we did was proving some laws of exponents, right? For example, one of the laws that we proved was that a to the m times a to the n equals a to the m plus n. Another law that we proved was that a to the m to the n equals a to the mn, etc. Okay, so we have done this with exponents so far. These are all the things that we have done. Okay, now let's move on and try to understand fractional exponents. Okay, so in order to understand fractional exponents, I need two things. I need to keep two things in mind. The first thing is this. We're gonna use this law, a to the m times a to the n equals a to the n plus n. And the second thing that we're gonna use is the definition of the n root of a. Okay, so since we already know this, and I believe I have already told you about this definition, but I'm gonna say it again. Okay, so I'm gonna go again over the definition of this number. Okay, so what is the definition of this number? The nth root of a. Let's first dissect each of these little symbols in here. Okay, remember this thing is called the index of the root. This symbol in here is called the radical symbol. And whatever you put inside the radical symbol is called the radicand. Okay, so these are just names. Okay, now what is the definition of that number? Okay, the n root of a is the number such that, colon, it is a number such that when you multiply it by itself, n times that is as many times as the index is telling you, what you get in the end is a. That is a definition. Again, the n root of a is a number with the specific property that when you multiply it by itself n times, you get a. That is a definition. There is nothing to understand about this. It's just a definition. Alright. So I'm gonna erase everything. And again, I'm gonna place the two things that I need. We know this. And the second thing is the definition of this number. We have these two things. Okay, now with these two things, I can start to understand what this symbol means. A raised to the 1 over n. Okay, and in order to know what's gonna be the meaning of this thing, we have to do a little experiment. It's a very simple experiment, and it is this way. Okay, what we're gonna do is this. I'm gonna multiply such number by itself. How many times? I'm gonna multiply it n times. The same number, I'm gonna multiply it by itself n times. Okay, So what's going to happen if I do this? I'm multiplying the same number by itself n times. And I want you to look at this law. One of the first laws that we learned, a to the m times a to the n equals a to the n plus n. And the question is this: can I use this law somehow over here? Can I use it? Yes. Why? Because we have the multiplication of two numbers with exponents that have the same basis, okay? And in this case, we have the same number being multiplied by itself. Okay, so this is going to be equal to a raised to the 1 over n plus 1 over n plus etc. plus 1 over n. How many times? N. N fractions all equal to 1 over n. Okay, I'm going to give you some seconds in order to understand why this is true according to this first law. I'm going to give you some seconds. Okay, I hope that it is clear that this is equal to all of this according to this first law. Okay, let's continue. This is equal to a raised to what number? What's going to happen when we add n fractions all equal to 1 over n? We're going to get 1. And if you don't believe me, let's do some experiments over here. Let's write, for example, two fractions that are equal to 1/2. Okay, what do you get when you add two fractions equal to 1/2? You're gonna get 1, right? Okay, what happens when you add three fractions all equal to 1/3? You're gonna get 1. And the same goes for any number of fractions all equal to, for example, let's do one more. Four fractions all equal to 1/4. What do you get in the end? 1. So n fractions all equal to 1 over n. It's obvious that we get. So that's why all of this is equal to 1. And basically, in the end, we have that this is equal to a. So in the end, we have proven that this number, a to the 1 over n, when we multiply it by itself n times, we get in the end a. And I'm going to erase all this in between method. Okay, all I want to keep is that result. I want to keep this result. Okay, fine. So this is the part A. I'm going to label this part A. We have discovered that this multiplication of factors n times gives me a. Now for the part B, let's consider one more time the definition of the n root of a. If you remember the definition of this number has the property such that when you multiply it by itself, n times, what do you get? You get a. Okay, so I want you to look at part A and this part B, okay, and tell me what is the next obvious conclusion. Look at them carefully, part A and part B. I'm gonna give you some seconds. Think a little. Okay, when you put together these two facts, you should arrive at the conclusion that a to the 1 over n is nothing but the nth root of a. This is the result that I wanted to get at. Okay, this is my discovery. A to the 1 over n is equal to the n root of a, and this is the discovery. Okay, so for example, when we write, I'm going to erase everything now. So for example, if you see something like this anywhere, 4 to the 1 over 2, 4 raised to the 1 over 2, what this means really is the square root of 4, okay, which we know is equal to 2. When we see something like this, 9 raised to the 1 over 2, what this means is the square root of 9, which we know is 3. When we see 27 raised to the 1/3, that's equal to the cubic root of 27, which we know is 3, etc., etc., etc. So basically, when you see any number, I'm gonna write now any other general number. Let's write 13 to the 1 over 6. Okay, when you see something like this, all that this means is nothing but the 6th root of 13. So basically, the discovery is the following. When we have a number raised to a fraction like this with a 1 as the numerator, the discovery is that all of this means the 6th root of 13, okay? And this is the index of the root, okay? More examples. I want you to understand this very, very well. Let's do 2 more examples. Minus 2 raised to the 1 over 8 is nothing but the 8th root of minus 2. 4 raised to the 1 over 13 is nothing but the 13th root of 4, and so on and so on and so on.